Okay, matter part 1. As you are watching this video, you should have out in front of you your text reading on matter part 1, pages 45 through 50. So maybe have that open up on your desktop as you are watching this. You can correct your answers or double check your answers to make sure that they are correct as I go through this video with you. Also, you will be filling in some notes on the Student Outline for Notes Matter Part 1. It is a white note sheet, printed front and back. You should have picked one of those up on your way into class today. Very good. Here we go. So, Matter Part 1. Everything, including you, is made of matter. Chemistry is the study of changes in matter. Now, these changes are due to an exchange of energy. Remember, we've already looked at energy in forces in motion and in electrical energy. So here we have changes in matter due to either adding energy or removing energy from matter to make it change in some way. Explain why visible light and electricity are not classified as matter. Well, visible light and electricity are not defined as taking up space or having volume. Visible light and electricity, well, visible light is made up of high-speed photons, which we'll discuss later, and then electricity is high-speed moving electrons. Since they're not in any given spot at any given time, they are not classified as matter or having volume and taking up space. All right. So, we're going to revisit the atomic structure. We already know the basic players here. We've talked about this briefly before. The proton is written with a symbol of a lowercase p and a superscript plus. Let me just put the proton here. And its mass in atomic mass units is something called 1. Scientists cannot measure an individual proton on a scale that we know of today, but we can give it a mass size based on its connection to size of other particles that make up the atom. So the proton has a mass number of 1. And of course the charge is positive. Neutron is the other particle that is in the nucleus of the atom. And the neutron, remember, is that cosmic glue that holds the nucleus of the atom together, hooking those protons which want to repel each other, forcing them to stay together in the nucleus. All right, neutron has an atomic mass unit of 1 and a charge of 0. No charge, nada. The electron symbol is a lowercase e with a superscript negative. Excuse me. The atomic particle, electron, we'll write it in there. The electron has a mass unit, atomic mass unit of roughly 1/1,800. So it's nearly 2,000 times smaller than a proton and a neutron. And of course its charge is negative. So why does an atom stay together? Why doesn't this want to fly apart? Everything's moving quickly, and the electrons are traveling at the speed of light, trying to repel each other. And the protons are trying to repel each other with the neutrons holding them together in the nucleus. So there's a lot of energy in an atom. So why doesn't it just go flying off into different directions? 3 main forces. One is the electrical force. This is where opposite charges attract. Thus, the electrons, the negative charges, stay in orbit around the protons, which have that positive charge. Opposite charges attract. Gravitational force. Every single bit of matter is attracted to each other in the entire known universe. The nucleus is 99% of the mass of an atom. So electrons are kept in orbit around the nucleus. Along with electrical force and gravitational force, there is that nuclear force. This is the neutrons acting like a kind of cosmic glue to hold the protons together in the nucleus. So number 4, what then is the difference between something we call an element and an atom? An element is a substance that cannot be separated or broken down into simpler substances by chemical means. That means if we force it to interact with other chemicals or atoms or elements, it cannot be broken down into anything simpler without losing its identity. An atom is the smallest unit of an element that maintains the chemical properties of that element. Such as an atom of gold will maintain the sparkle and yellow color of that metal we know as gold. As soon as you break apart the gold atom, you no longer will see that chemical property of shiny metal and yellow in color. So what is the difference then between something we call a molecule and a compound? A molecule is defined as a group of atoms held together by chemical forces. A molecule is the smallest unit of matter that can exist by itself and retain all of a substance's chemical properties. A compound is a substance that is made up of atoms of different types of elements. So each molecule then of a compound has 2 or more types of elements that are chemically combined. So when we talk about an atom and an element, we're talking about a single unit, a single element, a single atom. A molecule is larger. It is comprised of more than one element bonded together with chemical forces. And the compound cannot be broken apart or it becomes something totally different. So let's compare elements and compounds in our data table on our outline for our notes matter part 1. And in the space where you see the number 1, that is where we're starting. So in the element side, an atom then, as we're comparing it to a compound or a molecule, an atom is the smallest particle that has all of the properties of a specific element. A molecule is the smallest unit of a compound that has all the properties specific to that compound. The second part of this, element versus compounds, is this. When we're referring to specific elements in chemistry, we use a chemical symbol. A chemical symbol is used to represent an individual element, such as S represents sulfur, the element sulfur, K represents the element potassium, and so on and so forth. Now, why don't they use P, capital P, instead of a capital K? Well, there are a lot of elements on that periodic table, 92 natural elements, and when they were first being named a couple hundred years ago, they were given Latin names, a lot of them. So potassium has a letter that starts with K, and a capital P then would be a different element on that periodic table. In your text reading, you had this question to answer. Okay. And this question says, asks you rather, what is the most abundant element in the human body? The answer is oxygen. Does that surprise you? Oxygen is a gas. How can oxygen be the largest or most abundant element in the human body? Well, the human body is made up of primarily water. And oxygen is a very important part of the water molecule. In fact, 2 oxygen atoms are bonded to 1. Oh, I'm saying that wrong. An oxygen atom is bonded to 2 hydrogen atoms. And so we end up with also oxygen being found in all kinds of food that we eat, and it makes up our cellular structures. Okay, next. Elements versus compounds. A compound is used to represent a single molecule of a specific compound, H2O for water, etc. Elements versus compounds continued. Here's, we always, in a chemical symbol, we will write the first letter as a capital letter, and the second letter will be lowercase. In a chemical formula, we also include a subscript. A subscript listed after the element symbol is the number of atoms of that element found in that compound or molecule. So there's the H2O for water, and then CO2 for carbon. Now note that we have a capital C and a capital O. That tells us that we have 1 atom of carbon bonded to 2 atoms of oxygen. If you saw it written like this, with a capital C and a lowercase o, subscript 2, well, this is the chemical symbol for cobalt. So you just told me that you have 2 atoms of cobalt bonded together. Well, that's definitely not carbon dioxide. So again, be careful when you are writing out chemical symbols and chemical formula that you have the first letter of the chemical symbol for each element is capitalized, and the second one is always lowercase. All right, so let's define chemical formula. Chemical formula is defined as the chemical formula for water. If we look at this molecule in the picture, we have, again, 1 oxygen atom and 2 hydrogens. So you can see we have O1 and H2. Now, that looks different than the H2O that we are used to seeing when we describe water. This is the proper way of putting those 2 letters together, those 2 elements, in order to talk about the water molecule. OH, we start to get into something called hydroxyls. But don't worry about the order. Right now, we'll be going over that in more detail later. So let's identify the following as either an element or a compound. Sulfur, capital S. If there's only 1 capital letter, that means that that is actually an element. It's the chemical symbol for the element sulfur. Methane, we have 2 capital letters here. So now we know that we have a molecule or a compound made up of carbon and hydrogen. So this is a compound. Carbon monoxide has a capital C, capital O. Again, a compound. And potassium with a single K is an element. Looking at figure 6 on page 48, I wanted you to answer the following. How many different elements make up one molecule of indigo? So this entire thing here is one molecule of indigo. Now, how many different elements? Okay, well, here's carbon, because we know that because we have one capital C. We have hydrogen with one capital H. Now, if you don't know the names of these, C, H, N, O, that doesn't matter. All that matters is that you see there's a capital C. That means that's one kind of element. A capital H means a second kind of element. Capital N is a third kind of element. And capital O is a fourth one. So we have 4 different elements. Again, if you don't even know the name of these symbols, don't worry about that. You know there's 1, 2, 3, 4 different letters. That means you have 4 different elements in this molecule. How many atoms make up one molecule of indigo? Now, that's something interesting. Remember, the subscript comes after an element symbol, always and forever. So that 16 tells us we have 16 atoms of carbon. We have 10 atoms of hydrogen. We have 2 atoms of nitrogen and 2 atoms of oxygen. So we have 26 and 30. So we have 30 atoms making up one molecule of indigo. Holy schnolis. That is a huge molecule. What is a subscript in a chemical formula then? I just kind of went through that with you. But let's make sure you have that formal definition on your text reading. A subscript is the number of atoms of each element in a compound. And it is written as a subscript after the element symbol. If only one atom of an element is present, no subscript number is used. We call that a redundancy. If you say that I have 1 carbon atom, we don't need to put a 1 here because I already know you have 1 because you wrote the symbol. So don't put a 1 as a subscript. Only time you use a subscript is if you have more than one number of a certain element. Okay, 11, given the chemical formula then, C4H8N2O4, we need to figure out a couple of things. When we look at that, you can see that this letter, or number rather, in front of all of this should remind you of something in math. Okay, a coefficient, right? So if I isolate that molecule, the 4 in front tells me how many molecules of this I have. So this tells you you have 4 molecules of whatever this is, all right? What do the subscripts for 8, 2, and 4 tell you? Subscripts always tell you the number of each element in that molecule. Now, we're going to take a look at pure substances versus mixtures. A pure substance versus mixture. Refer to your text reading numbers 12 through 16 as you fill in notes on your guide sheet. So, on the front page of the guide sheet, outline for your notes, matter part 1. Go down to the bottom, there's pure substance versus mixture. Here we go. Pure substance is defined as matter with a fixed composition and definite properties. That means it can either be an element or a compound, but it has a fixed and definite composition. You can't change it or it becomes something different. A mixture is a combination of more than one pure substances. So you have pure substances, fixed composition, all put together to create something else. So it's all mixed together or connected together in some way. Number 2 on your sheet, the recipe for a pure substance cannot change. Sugar is sugar is sugar. Okay? The molecule C12H22O11 is not going to change. Even if I were to break this down a little bit, it would still end up being a molecule of sugar. This is just a rather large molecule of sugar bonded together there. Mixtures, on the other hand, the recipe can change and still be called the same thing. Italian dressing. You go into the grocery store, your mother says, oh, go get some Italian dressing and meet me over by the frozen fish. You go over to the dressing aisle and oh my gosh, there's like a bajillion different Italian dressings to choose from. But we know we call it an Italian dressing because it has the primary ingredients of oil, vinegar, and then spices. Those are the main ingredients of Italian dressing. Now this amount of oil, the type of vinegar, is it going to be, red vinegar, cider vinegar, white vinegar? Is it going to be what kind of spices? Garlic and basil or something different. So the recipe can change, but we can still call it Italian dressing. You try to change the recipe of your sugar, and you separate out this, now you no longer have sugar. Now you have carbon and water. You don't have sugar anymore. So, a pure substance, you cannot change the recipe. Mixtures, yeah, baby, you can change the recipe. So, 16 on your text reading asks, John and Sue are looking at a jar of honey labeled as pure honey. John says, well, pure honey has nothing else added. Sue says, it isn't really pure. It's a mixture of lots of different substances. Who is right? Well, part of that depends on a couple of things. This says wildflower, pure honey. So one would assume that this is what's coming out of the comb from the bee. But let's look at the comb of the bee. What's going in here is not honey yet. At first, what happens? At first, the honeybees pre-digest the nectar in their bellies before they bring it back to the hive. The bees have a tongue that is a lot like a straw and stores it then in a special stomach when they suck it in. This is called a honey sac in the bee, where it mixes with proteins, enzymes, that start to break down the nectar, which is water and sugar. Here a little bit better. Oh, I'll lift that up. There we go. All right, so honey then contains simple sugars. It contains minerals, vitamins, bee pollen. So you know those honeybees, when they're going into the flowers, they're actually picking up some of the oops. Here. Now why won't you go down there? There we go. Okay, so when they suck in that nectar, they have to go past those stamens that have the yellow pollens stuck to them, and they pick that up on their hairs that they have on their bodies here, and that some of that also gets packed into some little sacs on their legs, but I don't need to go all into bee anatomy and all that with you to make my point here. And then they have the enzymes in that honey sac that is working on all of that stuff and making it into a food that they then regurgitate into the comb. Regurgitate is a fancy word for they puke. They basically puke that out into the honeycomb, and then it collects in there. Once it's full, they then cap it with wax, which you can see this guy is going to get ready to do here. Yum! So all of that stuff, simple sugars, minerals, vitamins, bee pollen, and enzymes are all in pure honey or raw honey. Yay. Think about that next time you have some honey. Bee puke, Mom. Yum. All right, let's take a look at heterogeneous versus homogeneous. Refer to your text reading numbers 17 through 18 as you fill in notes on your guide sheet. So, heterogeneous mixture is a mixture with some or all of the parts visible. Some or all of the parts are visible. Homogeneous mixture is a mixture that looks uniform throughout. Mixing puts individual units or molecules between each other. Another word for that is it dissolves. It is also called a solution. Now here we have a plethora of all kinds of different items that I have collected on the internet. And what we're going to do is we are going to separate those out into heterogeneous mixtures and homogeneous mixtures. All right, let's see. Remember what a heterogeneous mixture is. A heterogeneous mixture is a mixture where you can see some or all of the parts. So here we have some strawberry jam. That would be heterogeneous. You can see some of the pieces of strawberry in there. You can see kind of something glossy and gooey-like in there. So we can see some or all of the parts of strawberry jam. Over here we have milk. Milk is a homogeneous mixture. If you look at milk from the grocery store, it looks uniform throughout. In fact, we call that homogenized milk, homogeneous milk. It has had some of the milk fat removed and maybe some carrageenan, which is a seaweed component, put in there to get it to be all uniform throughout so that the fat molecules don't separate out to the top, which is what cream is. If we take this spoonful of sugar and we mix it in some water, we know that if we mix it long enough, the water will become clear again. It's homogeneous. So that goes over there. Johnson's baby shampoo. In fact, a lot of shampoos are homogeneous. Dare I say, nearly all of them. Here's something. This is a beaker with some oil in it. Obviously, we can see the water and we can see the oil. That's heterogeneous. We can see some or all of the parts. Kool-Aid starts in a package. When it's in the package, you can see the parts. You can see pieces of sugar and darker colored flavor crystals and so on. But when you mix that together in a cup of water, it is homogeneous. We can no longer see all of those little particles. What about sand? Yeah, that's pretty obvious. This is heterogeneous. We can see some or all of those parts in that sample of sand. Chanel. Oh, perfumes. Yes, perfumes are homogeneous mixtures. Here are some soil samples. Soil samples look different. Heterogeneous. How about this one? Here's a glass of soda. You can see the bubbles bursting and particles flying up into the air above the drink. And you can see some ice cubes floating here. So the bubbles is carbonation in there, and then you have the dark colored liquid, which is the flavoring, and the ice cubes. So we have a heterogeneous mixture. We can see some or all of the parts. Paint, homogeneous. Salsa, baby. Yeah, salsa. We can see some or all of the parts. We can't see any parts of the can of paint or the paint, so that's homogeneous. Here is lotion. Lotion is homogeneous. So there, I hope that gives you some good ideas. And we will be challenging you in class to do some more of that organization. Immiscible versus miscible, that is on your text reading. Immiscible is when two or more liquids cannot mix into each other. It can't be done. No matter how you try, shake them up, they still will separate or stay separated within that environment. Miscible is when two or more liquids are able to dissolve into each other. So an easy example for immiscible is that salad dressing, Italian salad dressing. You see how the oil is separated out from the vinegar and the seasonings. And then miscible would be if you were to take water and vinegar and mix those all together, you would not be able to see individual molecules of vinegar or water. They will have been all mixed together and gone into solution. Now, flour and water don't mix. Would they be considered immiscible? Let's back up a tick. Immiscible, when two or more liquids do not mix into each other. Flour is not a liquid. Water is, but the answer is no, because flour isn't a liquid. All right, last section here. How mixtures compare with compounds. Parts can be separated by physical means when we're talking about mixtures. So, parts can be separated by physical means. That means we can pick them apart. Like the pieces of sand, we can separate out the little pieces of sand by color, which would maybe indicate what kind of minerals were in each of those little pieces of sand. We can evaporate whatever liquids are in there. We can put it out in a room and just let it evaporate slowly over time. Or we can put a fan over the top. Filters, we can pour it through a filter and that will trap some things and then let other things go through, so then we can kind of separate out some of that in that manner. Strainers, we could pour something that has some solids in it and liquids and have that water seep through, leaving behind the solids. So that would be examples of separating out physically by doing something like that. Now, for compounds, we need a chemical reaction. You need a lot more energy than just picking it apart with your hands or letting the air absorb it over time if it's water in there, and taking that away into the environment. So, what kind of chemical reactions are we talking about? Well, fire. Let's put a match to it. If it burns, we've got a chemical reaction happening. We put a log of wood on the fire, and an hour later you look inside of the fireplace and all you see are ashes. Well, guess what? It's not wood anymore. It has now been broken apart, decomposed by the fire into something we call ashes. And in the meanwhile, releasing or freeing up water vapor that was stuck in that molecule of wood, blah, blah, blah. Electricity, zap something with electricity. That will force elements to break chemical bonds. Or put an acid or a base. Bases, strong bases, can act like acids, and they can break apart chemical bonds. So, for a compound, you need a lot of energy. You need some kind of chemical reaction to break it apart. Mixtures, a lot easier, much simpler to separate them out. Again, mixtures, remember, have a composition or a recipe that can vary from mixture to mixture and still be called the same thing, whereas compounds, you cannot. Compounds have a definite composition. Okay? Water is always and forever going to be H2O. You break that bond, zap it with electricity, and now you have hydrogen gas and you have oxygen gas. Okay. NaCl. Na is sodium, Cl is chlorine. Chlorine is a gas. You break that bond, you release this chlorine gas, and you release the sodium, which is a solid, and so on and so forth. All right, now it's quiz time. I want you to stop, pause this video, and try to do the quiz on your own, which is at the bottom of the back of your note page, your white note page, and then check your answers as I go through them in the next slide. So pause it. Now I'm going to move on. Which diagrams below could represent the following 5 things? Now, I gave you a clue. Each circle represents one kind of element or atom. So, number 1, a mixture is more than one kind of something put together. And that something I want you to focus on is elements. So an element equals an atom. So there should be only one circle because that represents a kind of element. But now I want a mixture of single atoms. A mixture of single atoms. And so our answer here is letter B. Okay. So here we have one kind of atom, and here we have a different kind of atom. So you have more than one kind of atom put together in that space. That is a mixture of elements. Which box is containing or holding a pure molecule? Molecules are more than one compound, or element rather, bonded together. That can be the same element, atom to atom, like you see here. Okay, so that's one compound. This is a second compound. This is a third one, but you know what? The color of that circle tells you they're all the same. So this, C, is your pure molecule. Yeah. Pure element, this should be easy now. Pure element is A. Okay. All the same element, only singletons here. Pure element sample. And now we're down to 4 and 5. 4, a mixture of compounds. Compounds are more than one element bonded together. And now a mixture is different kinds of these compounds. So that would be letter E. Here's one kind of compound. Here's another kind of compound. So E is correct. And then by default, of course, we have D for the last one, which is a mixture of single elements and compounds. Dun, dun, dun. All right, now what you have to do is take your filled-in white student outline for notes, matter part 1 sheet to your teacher, that would be me, and have me check you off. Good job.